All right. I guess it's 1 p.m. in Central Time, so let's get started. Hello, everyone. Welcome to our C.R.E.A.T.E UTC webinar series. My name is Xijun Jeff Shi. I'm the Technology Transfer Officer for the C.R.E.A.T.E Center. I'm also an assistant professor at Texas State University. Today, we're very pleased to have actually two speakers to talk about some recent updates on two C.R.E.A.T.E-sponsored concrete innovations. The first innovation is Plient fibers, and the speaker is Dr. Charles Donnelly. Dr. Donnelly is currently a postdoc researcher at Texas A&M University. He earned his PhD from the University of Pittsburgh, where he studied concrete pavement performance. Dr. Donnelly is also VP of Engineering of Circle Concrete Tech, which is a startup company that I'm also involved with. The second product or innovation is SEAHIVE. Dr. Landolf Barbarigos at the University of Miami will present SEAHIVE. Dr. Barbarigos is an associate professor at the University of Miami. He has a PhD degree in EPFL, and he also did his postdoc research at Princeton. He has received a lot of awards, including NSF CREAL and ACEMFL Rising Star. So both of the speakers have pre-recorded video, and I will play it for next about 53 minutes. After presentation, we will have about 5 minutes for Q&A, and both of the speakers are here to answer any questions. So without further ado, I'm going to play the video right now.
Good afternoon. My name is Charles Donnelly. I'm a postdoctoral researcher here at Texas A&M University. I'm also the Vice President of Engineering at Circle Concrete Tech. I'd like to thank Dr. Shi for inviting me and giving me the opportunity to participate in this C.R.E.A.T.E webinar series. Today, I'll be sharing some really exciting work that we've been doing over the past couple of years at Texas A&M, and the title of the presentation is Plient, Recycled Steel Fibers for Concrete. So as engineers, we're oftentimes thinking and focused on different structures that are key parts of our infrastructure systems, which affect the general public. And these structures include buildings, dams and roadways, as well as coastal protection systems. And a key component of all of these structures is the materials that we're using to build these. And by far, the most widely used material for construction is concrete. It's the most used artificial material in the world, and it's estimated it's around 30 billion tons of global production. So what this means is that any opportunity to improve concrete materials offers a great opportunity to improve the durability, performance, costs, and sustainability of structures, everything from a roadway to a building floor to a dam or a levee section. So any opportunity we have to focus on that is great. And one thing that we know about concrete is that oftentimes it requires additional reinforcement, whether that's a steel rebar or in many cases, using fibers in the concrete to improve the overall performance of it. And fibers are a proven technology that are used with a number of benefits. And these benefits include controlling the cracking due to plastic shrinkage, enhancing the flexural and tensile strengths. It's also improving the toughness of the concrete to improve the long-term durability, delaying crack formation by delaying the formation and growth of microcracks, improving post-crack ductility, and bettering the impact resistance. And so fibers have been around for decades in concrete in a number of different forms. These forms range from a manufactured steel fiber, like the one shown on the left, naturally forming fibers, or synthetic fibers such as a plastic or a polymer fiber that have been used in concrete in different applications to improve it. One of the areas or one of the solutions that are often offered is metallic steel fibers, such as the one on the left there, because they've been shown to improve the toughness of the concrete and are also very effective in resisting crack development and propagation. So although fibers are really great at improving a lot of the concrete material properties, there are some limitations that are critical And those include the high cost associated with constructing sections with these fibers, but also the sustainability and environmental impact because of high CO2 emissions with the steel fibers. So this is where Plient concrete comes in, because it offers a solution that utilizes the benefit of a lot of these fibers and mitigates some of the limitations. So what is Plient concrete? So Plient concrete is traditional or standard concrete, which incorporates Plient fibers into the concrete to offer all those improvements which I previously mentioned. Plient fibers are derived from a recycled steel product, and here's an example on the top there of the Plient fibers, and they can be seamlessly integrated into traditional or conventional concrete to offer the benefits of different fibers. So as I said, Plient fibers are a recycled steel product. Their composition is essentially almost entirely of steel from their recycling process, but there is some residual rubber and textiles left over. It's a good breakdown on the bottom left there showing kind of a mass of the Plient fibers, showing fibers of different lengths and diameters that are made out of steel, and then kind of interspersed throughout some residual rubber and some textile. Something that's unique about Plient fibers compared to a manufactured steel fiber is that because of the recycling process, there's, as opposed to be a uniform length and diameter of the fibers, there's a distribution of the lengths, diameters, and therefore the aspect ratios. So Plient fibers are an effective fiber solution for two key reasons, and both of them have to do with the interface between the fiber itself and the concrete or the cement matrix. So the first reason is because of the recycling process, there is some residual rubber that remains on the surface of the fibers. And there's a really good image shown on the left there, showing a zoomed in image of the fiber, and you can see the surface of the fiber is coated with some residual rubber. And what this residual rubber does is offers a texture to the fiber that improves the bonding between the fiber and the surrounding cement matrix. And then the other reason that the fibers work well is because of the bends in the fiber. So because of the natural recycling process, the fibers do not come out straight. There's some angularity to it, and these bends vary between the fiber lengths. But the important thing about it is both the surface texture from the residual rubber and the bends improve the interface between the fibers themselves and the surrounding cement matrix. And this is key for the actual performance of the fiber because improving the bond between the fiber and the surrounding cement matrix results in a better performing fiber that can achieve all those properties I mentioned earlier, whether it's the improved strength, the post-crack performance, and the durability, and so on and so forth. So there's some key benefits of using Plient compared to standard reinforcement methods or alternate fiber techniques. So first is a key question whenever you're looking at introducing a new material is the cost. So Plient fibers offer up to 50% less cost than conventional reinforced concrete. And this is achieved by replacing rebar or mesh and stirrups in the construction time with the recycled steel fibers. Additionally, because it's a recycled product, the second key advantage is the environmental impact. So because this is a recycled product that's replacing a manufactured rebar or steel fiber, there's 7 to 19 times lower carbon footprint associated with Plient concrete compared to rebar. Additionally, there's 15% lower carbon footprint of the Plient fibers compared to some of the manufactured steel fibers. The third benefit is reducing the labor and the time of construction using Plient fibers. So in many structures that use a rebar mesh or a rebar that's tied, you have significant construction time associated with the placement and the tying of the rebar. By using Plient fibers, you're able to eliminate all of that construction time, thus speeding up the construction process. The fourth benefit of Plient fibers is the improved durability and long life of structures using Plient. So because Plient improves the cracking time, you get a much tougher and much more resilient structure, and you get less degradation because of the higher impact toughness of the Plient concrete. And lastly, the last benefit of using Plient is an improved process integration. So anytime you're introducing a new technology, a concern is obviously how can we integrate this technology into existing construction practices so we don't have to throw off or necessitate significant changes. The benefit of Plient is we're able to integrate this directly into the concrete. and it's simplified process compared to other steel fibers, which come in bags and require very labor-intensive dumping the bagged fibers in the back of the concrete truck. We're able to directly integrate the fibers in and make it more seamless compared to other manufactured steel fibers. I briefly touched on this, but I think this is a great plot to show, is that one of the key benefits of Plient is the significantly lower embodied carbon associated with Plient compared to other reinforcement alternatives. So in the plot here, you see the embodied carbon, tons of carbon dioxide per ton of the material, and you see Plient, the bottom left there, is significantly lower than existing manufactured steel fiber alternatives, the two in the middle there, as well as, and this is critical, is the rebar alternatives that are currently used on many projects. So Plient fibers have up to 19 times lower carbon footprint compared to alternatives, including the rebar reinforcement. So I'm making a lot of claims about the benefits of Plient fiber and all the great things it can do, but I really want to highlight that all of the research that's been done with these Plient fibers is backed by a significant amount of time and energy. Over 4 years of lab development that have been funded by a number of agencies, including NSF, ACI Foundation, NCHRP, and then Texas A&M Innovations. And what these projects that have been funded for these different sources have focused on is evaluating the key material properties of Plient concrete to identify the benefits of using Plient fibers compared to alternatives, and to be able to support and back up the benefits of these of Plient. So the properties that have been evaluated include fracture properties, flexural properties, split tensile strength, compressive strength, stiffness or Young's modulus, as well as crack performance and characterizing the individual fibers themselves. So I'm gonna go through some of these material properties and the results and identify individual areas in which the Plient fibers in the Plient concrete compares to traditional concrete. So the first area is in the pull-out strength. So as I mentioned earlier with the surface characteristics, an important characteristic of any kind of fiber is how well is the bond interface between the fiber itself and the surrounding concrete. So tests were performed at Florida State University, comparing Plient fibers to traditional or standard manufactured steel fibers. And using a fiber pull-out test, it's been shown that the Plient fiber has 500% better pull-out performance compared to the manufactured steel fibers. This is critical because as a crack starts to form and open up, the fibers are holding the crack tight and improving the long-term durability of the crack itself. And by having a higher pull-out performance, the Plient fibers are able to more effectively keep the crack closed and maintain the durability of the structure. In addition, there's been a number of tests done to evaluate the effect of Plient on different strength parameters, namely compressive strength, shown in the top left, modulus of elasticity or stiffness on the top right, and then the splitting tensile strength shown on the bottom. The key takeaway from these results is that using Plient in different dosages can slightly increase your compressive strength and has minimal effect on your modulus of elasticity, but critically, increasing your Plient dosage has a significant effect on the splitting tensile strength. So that plot on the bottom there shows that an increase from no Plient fibers shown in the reference concrete to 1 or 2% Plient fibers can show an increase of splitting tensile strength, resulting in as high as a 50% reduction, or I'm sorry, 50% improvement of your splitting tensile strength. In a comparative study, the increase in splitting tensile strength was compared between the Plient concrete as well as concrete reinforced with the manufactured steel fibers. And it was found that using a manufactured steel fiber with a similar size reported only a 37% increase in the splitting tensile strength. So again, not only is the Plient fibers improved compared to standard concrete, but it also shows improvements compared to currently on the market manufactured steel fibers. A key area that Plient offers benefits into is the flexural strength. So as we know, concrete often fails in either flexure or tension, and many elements that are used in construction, such as slabs or beam elements, the flexural strength is the critical parameter that we look at. Here are some results from 7-day testing using 1609 beam tests. On the left there, you see the flexural strength test results. And on the right, you see the residual strength, the post-crack performance. So on the left, you see that increasing the dosage from a reference or no Plient fibers to as high as 130 pound per cubic yard. You see a significant improvement in the overall flexural strength. But then critically, when you compare different dosages of Plient fiber, you get significant residual strength achieved through using Plient fiber. So an unreinforced or zero dosage of Plient fiber, which isn't shown in the plot here, you would have no residual strength. So once the crack forms, the beam breaks. When you look at starting to dose with Plient fibers, increasing the dosage to a certain point significantly improves the overall flexural strength or residual strength of the concrete. Another area where Plient offers significant benefits is the toughness of the concrete. Concrete toughness is a parameter which is significant when looking at long-term degradation of a concrete structure, for example, pavement structures at the joints, preventing spalling development and making sure that the structure is able to be durable for the long term. Improving concrete toughness is extremely beneficial for ensuring the long-term durability of the structure itself. And you can see that increasing the Plient dosage offers significant improvements in the toughness of the concrete itself. The last material property that was evaluated that I'm going to share is looking at shrinkage cracking. We know that as concrete setting, there's going to be plastic shrinking that occurs, and the plastic shrinking, when restrained, as most structures are in some way, leads to crack development. So the incorporation of Plient fibers, it's beneficial if we can reduce cracking development or at least mitigate its development. So a series of ring tests were performed. Essentially what a ring test is inside this test setup here, there's a central steel ring, and an outer ring is placed with a gap between the two rings. The Plient concrete is poured into the gap between the rings and allowed to initially set, at which point the outer ring is removed. There's a series of strain gauges on the inner ring, which measure strain development as the concrete is starting to cure and set. And as the concrete is setting, it's starting to shrink. And we can measure the strain development in the ring and estimate as cracks start to develop. We see drops in the strain as it's able to be released slightly. And we can compare the trends between the strain development in time between reference concrete, which is concrete that has no Plient fibers, and a dosage of 2% Plient fibers. And what we see is, first, the Plient fibers are able to achieve significantly higher strain development, but critically, we see a delay in the crack formation due to the Plient fibers, which is showing the Plient improves the shrinkage crack development over time. So I've talked a great deal about all these different material properties and the benefits of the Plient fibers. But the next question is basically, how can we actually use these Plient fibers in action? How can we see them benefit in different structures? So I'm going to give some examples of Plient fibers in action in a number of different structures and show how they're able to be seamlessly integrated into the construction methods. The first example I have are some precast pipes and junction boxes. So this is kind of an area where it was first explored using Plient fibers. Current construction practices for both the pipes and the junction boxes often require either a steel mesh or a steel wire cage, which is expensive and time-consuming to construct. So the opportunity to incorporate Plient fibers offers the benefit of eliminating those reinforcement techniques, but it's required that they have similar performance for both structures. So on the left here, you're on the top here, you see full-scale pipes and manholes cast using a dry cast method. And these have the Plient fibers integrated throughout. What was observed was great dispersion of the fibers and stable cast conditions. And it was very seamless to integrate the fibers into it. I have a cool video coming up that I'll show you that. Additionally, concrete junction boxes were constructed with up to 1.5% by volume Plient fibers. And it was observed that we were able to achieve easy fiber integration and improve the control box strength compared to the typical wire mesh reinforcement. Here's a neat video of the dry cast method of the pipe. So this pipe is being constructed with the Plient fibers integrated in. And as you get closer, we'll see that there's seamless integration of the fibers. And actually kind of cool is in the background, you can see the typical cage or mesh that they would use for the pipes, which are eliminated by using the fibers. And you can see that there's no fibers on the surface. It's a stable construction, and you don't have any fibers sticking out or anything like that. It was able to fully disperse and integrate into it. So in this sense, Plient fibers were a huge success with using these pipes, and shows that it can be easily integrated into that construction process. The next area that Plient offers an opportunity to be integrated into is in pavements and flooring. So in standard or traditional slab on grade, there necessitates mesh or rebar being placed. Again, that's very time consuming, costly, and labor intensive. But we found that Plient fibers can be integrated into this and cast using a volumetric or ready-mix trucks with no adjustments to the construction process. The performance of these slabs are quite well, despite applications of heavy loads, and the finishing quality is excellent. So we've actually conducted several pavement pilot sections constructed with Plient fibers, and there's been some great performance shown from that. So I want to share some videos. So here's some examples of them constructing a test section. On the left there is them constructing a test section right outside of a ready-mix concrete plant right here in the College Station area. One of the cool things about the way this was constructed was actually they constructed two sections side by side. One was constructed with Plient fibers, and the one directly adjacent, which is the one you see them constructing now, was constructed with traditional reinforcement. And the benefit of this is able to compare side by side Plient fiber performance and your standard traditional reinforcement method. Also, there's the same environmental conditions, and this is placed right before they're loading the concrete trucks. So all day you have heavy loads going over the slabs. So you get a lot of potential for degradation. So you can evaluate that. So here's them actually constructing the slabs. So you see this is Plient integrated in the concrete. You cannot tell at all that they're able to move the concrete around. We don't have any issues with dispersion or flaking or anything like that. The other benefit is that the Plient fibers do finish quite well using standard finishing practices. Here's a neat video of them using the power ski and just going across the whole thing, and no issues with fibers sticking out or anything like that. You honestly can't even tell if the fibers are there. So lastly, looking at some of our test sections that were constructed about a year ago. Again, these are the sections that are side by side with one another. The Plient reinforced concrete, in addition to being more cost effective and faster, we're seeing no degradation at the joints. You honestly can't even tell if the fibers are there. The Plient fibers have performed very well throughout the slabs. We don't see any slab cracking or loss of performance. Directly next to it, on the other hand, is you have the conventionally reinforced pavement. We're already starting to see some joint spalling, and this is due to the lower toughness of the concrete. And this is a real problem because over time that joint spalling is going to continue to get worse and worse, and as the heavy vehicles go over it. So a really cool example of two different constructed slabs directly adjacent with the same vehicle loading, and it's showing that the Plient fibers are performing great. So a great opportunity to compare those two. So as I kind of wrap up, I want to share some of the current work that we're doing, looking at the Plient fibers and how we can integrate them. We're happy to announce that recently we were awarded an EPA SBIR project. So it's a 6-month phase 1 project that just began in December of 24. The focus of this project is being able to develop pumpable mixture designs using Plient fibers. Again, we're really focused on opportunities to seamlessly integrate the Plient fibers into existing construction techniques. And as you can see on the right there, oftentimes when they're constructing slab on grade or slab on deck, they're pumping the concrete. So we're demonstrating that the Plient fibers can be integrated into the current construction techniques to be pumped directly on job sites. The other area that we're working on has to do with dosing systems. I mentioned briefly a little bit early on that one of the benefits of Plient is it eliminates the need for dumping bagged mixes into ready-mix concrete trucks. And what we're working on is developing a system that can integrate or dose out the Plient fibers directly in the back of concrete trucks, and we can ensure the accurate dosage of our fibers as needed. So some exciting work being done, and hopefully we'll have some updates in the next couple of months for everybody. But I appreciate the opportunity to share some of this work. We're really excited about what we've been doing, and we're looking forward to having more exciting updates. Appreciate the opportunity to share this. Feel free to ask any questions.
Hello, everyone. I'm Landolf Rhode-Barbarigos, an associate professor of civil and architectural engineering at the University of Miami. Today, I will present you about SEAHIVE, the original project that led to our current research in the center. SEAHIVE was funded by the Transportation Research Board under NCHRP, the National Cooperative Highway Research Program, IDEA project number 213, in collaboration with the Florida DOT. As you already know, many of us, almost 40% around the world, like living close to the shoreline. We love water and the connection that we have with water, but it's also practical, let's say, issue, as these cities that developed historically have this connection with water from logistics to the personal, let's say, pleasure that we get being in such a nice environment. However, we all know that living close to water, sometimes we have to weather the storms. This is a picture from Hurricane Irma here in Miami, and you can see the conditions are completely different. And we currently know that with climate change, storms will become stronger and more frequent. And we need to protect ourselves and our infrastructure from the impacts of these storms. Here is a graphic from NOAA with respect to those disasters, and it includes a lot of disasters. So on the left vertical axis, you have the number of events. On the x-axis, you have the years from 1980s. And on the right vertical axis, you have the cost of these disasters. I want to highlight that you see that the number of events increases. The cost also of those disasters has been increasing. I want to bring to your attention two colors there. The yellow color, the yellow bar there, which is tropical storms. So we see that the tropical storms, the impact of those tropical storms increases. And also the blue one, which is flood. These two are very relevant for us in our center. Here I'm highlighting what is happening in Florida. This is for tropical storms. So you can see that Florida leads basically the cost of disasters when it comes to tropical storms. And the rest of our center, of course, is also well positioned, unfortunately. Kind of like the same idea, but this is flooding in general. You can see also the statistics there. So flooding is also a big problem. And of course, it's linked sometimes with tropical storms. Other times is due to other events. However, this is not a problem only for our center. This is a problem worldwide. And here you have all the flood exposed cities around the world, highlighting some of these big cities there. So this is a well-known problem, I would say a universal problem, that it seems to exacerbate with time. Now, what is happening to the coastal cities is affecting, of course, the coastal communities. It's affecting the built environment and our infrastructure. And we often see pictures like this, where our transportation network, which is sometimes very close to the water and our first line of defense, is actually suffering from that. So we know that more than 60,000 miles of coastal highways are exposed to these events. And these are some pictures from here in Florida, where we understand that we're in a vulnerable position and we should actually do something about it. So the first thing is to understand the problem. So we have three damage mechanisms. Flooding is one of the damage mechanisms that everybody understands. So that's when the water comes in and we basically walk on water. And this is affecting both, can have some structural, I would say, problems, but is also affecting our operations, the service aspect. Erosion is when the sediments are removed, and this can cause significant problems in terms of instabilities. So you can basically lose structures. We've seen those houses and those roads, houses that are basically floating in the water, and works and roads and other works that are basically collapsing. And there's also wave action, which is sometimes forgotten, but not always, in the sense that we have that impact load, that huge force that is being applied on our structures and infrastructure. The rule of thumb is that waves of 3 or 4 feet, repeated waves, can break a small house. So how can we protect ourselves? There are different philosophies out there. Right now, there's a lot of discussions about our gray infrastructure, how we can harden and protect the built environment and the infrastructure by creating structures like seawalls, breakwaters, that are basically structures, human-made structures, that will absorb that before it reaches our valuable infrastructure. The other side is a more, I would say, a soft approach, is using nature-based solutions, local ecosystems. It can be seagrass, it can be oysters, corals, mangroves, and create basically spaces, natural spaces that will absorb that in a natural way. Given where we are today, I would argue that the Holy Grail is somewhere in between. We need gray structures that work with green structures, so a green and gray hybrid solution that promotes basically habitat. And this is the design challenge that we're facing today. How can we design coastal protection and create habitat? And this will, of course, take different shapes and forms depending where we are with respect to the local, I would say, ecosystem, but also with respect to the needs of each community. Before I go into what we did with respect to SEAHIVE, I want to highlight why this is important. We know that green infrastructure, local ecosystems provide protection. However, to provide that protection, they need space and they need time. They need to establish, they need to grow. They also provide a lot of other benefits outside of protection, which are equally important. But the problem is that right now, we have this great need for coastal protection. And I argue we don't have necessarily the time to wait for this to establish. So a difference in the benefits is with respect to when those benefits of coastal protection are provided. With gray infrastructure, the moment we finish the construction of a project, we get that layer of benefit. However, of course, we know that our infrastructure is degrading, and we know that, of course, it's inert to a certain extent. So if we could provide structures that have that gray component and ensure that we get that protection from the day that the project is finished, and then accommodate a local ecosystem and have this growth inside our structures and provide biodiversity and provide regeneration and habitat, that would be basically the best of both worlds. The problem that we're facing when it comes to that is historically we've been designing thinking about people. So we put ourselves in the center as a design driver. So when we design structures, we think about what we like and how we operate. So the forms that we take are forms that align with our needs. The materials that we use are based on those forms and how also we interact with those structures. And of course, the forces are linked to those things. And now the paradigm has to change because nature has to become the center of this. So we need structures that work with nature. That means we have forms that align and work with nature, materials that can accommodate and provide growth to nature. And of course, the forces have to abound to this. This is what we focus around SEAHIVE. So SEAHIVE is inspired from nature in the sense that we use the hexagonal shape of the beehive. We use hexagonal reinforced concrete units to protect ourselves from the impacts of the waves and water. And the use of the hexagonal shapes is very important for us. It provides not only protection, but also a smart way of using the materials. The hexagon is one of the three geometries that provides a continuous tessellation. So when you put hexagon together, there is no gap. This is very important for stability purposes. So it's a stability issue, but it's also a very sustainable way of using the material because we maximize the empty space. So the hexagon gives you the maximum volume for a given amount of material. Our units are made out of concrete, as you can see on the upper left side, and we have also those perforations on the side. Those perforations allow the water to go in the system, and it doesn't reflect back the energy of the waves, but the wave goes in, the water goes in the system, spins, we have turbulence that creates, and basically we absorb energy within the system. This is great because in natural conditions, those perforations will also create channels. So marine life can create habitat there. So there will be fish that swim around and sometimes sediment also that transfer inside. And of course, we can parameterize that. We can have different different perforation sizes and different shapes as a system. So when we create those tessellations, and with respect to the forces, we actually tested that in SUSTAIN. SUSTAIN is the wind wave tank at the University of Miami. We can create wind and wave conditions up to category 5, and we can have different waves that we can send to scale models to understand that interaction of the model with the water and the waves. So we start 2000, this is the history of SEAHIVE. We started in 2018 with federal funding from NCHRP. Throughout 2020, we were doing tests in the tank to develop the concept. In 2021, we secured some pilot projects here in South Florida. And now we're working in concluding those projects. There are some that are still in progress. Now, what is interesting for us is that we had this collaboration with the local communities that are looking for solutions. On the same time, we were lucky to intersect with other projects from inside the university, but also outside with projects like the DARPA Reference Project and another effort, the Army SBIR on 3D printing. So these are projects that actually overlap with SEAHIVE or use some SEAHIVE component. And they show how basically this project has grown organically. And right now we're seeking different, let's say, components of that research and development in various fields, including our own sensor. Now, we started with testing different shapes. So we had here a square, a circular, and a hexagonal cross-section. And we did different patterns from solid to perforated. And with the perforation, we tested basically different perforation percentages, but also different patterns to absorb that perforation. So you can see here there's, of course, a solid version, one which is with small perforations, one which is with large perforations, but also combinations that give you the same percentage of voids. And what we were doing is we were measuring the impact of the design and the perforations in the interaction with the waves. We did testing in the tank of the system. So what we did is we created mini walls and mini reefs made out of the SEAHIVE, and we were throwing waves and doing water level measurements before and after sometimes, or just before, to assess the performance of the structure and the interaction of the structure. What you see here is part of our testing for a seawall with a step seawall with SEAHIVE vertical elements. And what we were measuring is how much reflection do we have. Reflection is important because sometimes it amplifies the negative effects, but also for scouring and other issues. And sometimes we're doing testing with respect to the energy dissipation. So the fact that we have a hexagonal prism basically reflects at multiple directions. And of course, we also absorb with the perforation some of the energy inside the system, as we were discussing before. So this reduces the energy that bounces back into that. So we started thinking about this, and we started other applications also. So we can do submerged structures like breakwaters. And we did a comparison of a SEAHIVE variant with a trapezoidal reef. There we were assessing how much of the energy is absorbed by that reef. Is it inducing wave breaking? And what is the energy inside those perforations? As I said before, we had the chance to have this collaboration with our local communities here in South Florida. And one of the projects with one of those communities was SEAHIVE. SEAHIVE was a University of Miami ULINK project funding in collaboration with the city of Miami Beach. So this is of course, this is a picture that we made where the idea was to create an artificial breakwater populated with corals. And the idea here is about artificial coral reefs and using them to not only promote restoration, but also protect the coastline. So SEAHIVE was actually a project, a pilot project that was made real. And this is the picture of the SEAHIVE units, the first day of the deployment. You can see that they're very nice stacked, very clean, very nicely put together. So this is offshore of Miami Beach, just at a depth of 14 feet. These structures now have been there for almost 2 years, close to 2 years, a year and a half. And these are some pictures that were taken recently. My colleagues call them a lot of times fish aggregation devices, in the sense that fish love them. They love that macro scale complexity that with the perforation is created. And we also use those structures to make local measurements of the waves. So we had a campaign with different instruments to see the absorption of the waves and the currents around them. The structure is, of course, small, so we have to do very localized measurements, but still they satisfy the purpose of the experiment, which is to see both the impact of the corals and the growth of corals on them, but what is their impact on the waves and the water around. Now, at deployment here, you can see how the surface and the texture has changed and how recruitment has occurred. So, of course, we had our concrete, let's say, surface, nice and clean on the day of the deployment. And as we went with time, we started seeing the recruitment of different organisms there. So we've been monitoring not only the growth of corals that we transplanted, but also the different recruitments on the surface. And sometimes these are even competing with the purpose of the coral growth. When it comes to corals, we were actually planting more than 500 corals on this, and we've been measuring the mortality and growth of those corals. I'm happy to report here you have a picture of the way after 1 week and after 2 months, you can see that there's already the growth. And I'm happy to report that although we had some very warm, let's say, waters over the past years, we had more than 80% of survival in our reef. This is because our colleagues are transplanting heat-tolerant corals. So we can actually, when we want to combine gray infrastructure with green infrastructure, what we combine and how we combine things is equally important. It's part of that design challenge that we have. Now, this is a more recent picture. You can see here that there is growth, and you can see some devices that have related to the corals, some corals on the top. But I want to highlight that living component of the reef. Now, SEAHIVE is not only for breakwaters, and we had the chance to co-design another, let's say, pilot project with the city of Pompano and Broward County and a local nonprofit, Shipwreck Park. These are our collaborators in the project that we call Wahoo Bay. Wahoo Bay is a marine park for educational and research purposes, and it includes that artificial living shoreline. The idea was to use the sea hives to absorb, of course, the impact of the waves and protect the park which is next door, but also to host mangroves. The project started in a different with a different idea. So they were envisioning to have this 10 feet diameter culverts that will accommodate the mangroves. But we had an interaction with them, and our visions aligned so well that they allowed us to co-design with them the park and use SEAHIVE. What you see here on the right side is also the survey of the site, which includes seagrass. So we have some restrictions with respect to the extent that we can go in the water. So these are important parameters because they highlight also the usage of the system and the advantages of the system, which does not necessarily require a full footprint for stability purposes. So SEAHIVE has some advantages when it comes to that. So this is what we proposed for the SEAHIVE. So it has a component which is submerged. And then on the top, you have basically those units that accommodate sediment and will host the mangroves. The top unit there was designed so that it lies between the mean high water and mean low water and the intertidal zone. So it's kind of optimized for mangrove growth. This is some images that we created in terms of what we envision the space to become. It's if we get there, it will be, of course, a great success. But the project itself and how we get there is also a very important parameter on the development of SEAHIVE. So co-designing with the local community is very important because we also need to communicate the research and the aspects of that research. So designing and transferring technology is two, I would say, challenges that occur at the same time, but maybe not of the same nature. So we've been working also on communicating what we're trying to do to the local community and, of course, the general public. So we created and we started with some of our students also how we do that. So there was this study about how to communicate what we're trying to do at the local park through a series of visualizations and drawings and creating a path that guides you on where we are, what are the mangroves, where are the mangroves positioned and why we find them there, what is the green-gray infrastructure, and how does the climate affect what, and what can we do as citizens. So this is during the construction, a picture during the construction of the Wahoo Bay. So this is the first phase where we put the units there. And I think it's equally important to acknowledge that the construction process has a lot to do with a successful deployment of technology. So SEAHIVE has these hexagonal units that kind of sit into one another, so it's easy to deploy with other ideas that we have currently with clustering, creating larger units that include multiple SEAHIVEs connected together. This could be even easier, but having that process in mind, understanding the local conditions, testing allows us to actually be confident about our project, but also seeing like the materiality, the scalability, the robustness of the system, both at the production, but also at the deployment level. This is a picture from inside one of the Wahoo Bay SEAHIVEs taken from the county. So this was to report the natural recruitment of oysters in the site. And we do some surveys, pre and post, of course. And here this survey is about the fish. And we can see that post-installation, we have a lot of more fish on our sites. And we have two control sites, one which is directly next to our deployment and another site which is in a neighboring community. And what we are trying to assess is that habitat creation aspect. So not only we are looking at the performance in terms of the protection, so this we'll do in the lab, but also with measurements of wave energy on different sites, but also like how can we claim habitat? And it's early to say, so we will need at least minimum 2 or 3 years of data to claim that we did a good job in terms of habitat creation. But these are already good signs of this. Now, this is the other part. We started planting the mangroves. So these are propagules that we're planting on the top. You can see here we filled some of the gap with sediment. There's a fabric there that allows the sediment to stay in place, but also allows the exchange with the water. And we're still working on that. There are some challenges that we didn't anticipate, but we're learning a lot. And this is the important part with the pilots. Having pilots with the local communities allows us to assess different aspects from the regulatory uh, permitting, I would say, uh, challenges to the implementation and the construction to other aspects like this. But it's very important for us to be able to assess what is needed in order to create those sites that guide the development, the research and the development of any new technology. Now, we have some new projects and new ideas in the making. This is one of them. So first of all, we parameterized the design of the SEAHIVE, and we also create some hybrids. So this is a SEAHIVE where each side of the hexagon has a different composition of perforations. So with one unit, we can create different, you can say, facades of the design. We can also run piles. So this allows us to enhance the stability if needed at certain sites. On the same time, we've been continuing to do testing. So here, these are some tests that we did for the DARPA project. You can see that we have a breakwater with 6 SEAHIVE units. This is at the 1 to 20 scale. And what we do every time with our SEAHIVE project is we run the perforated and the solid configuration. This is because we know that through time and with habitat creation, sediment accumulation, the perforation, the voids that we have might get filled. So the perforations might not be at the same level. So we know that performance depends on perforations. Our perforations enhance the wave energy dissipation, but on the same time, our lower bound will always be the solid. So by running the solid versus perforated at different conditions, we can assess and have that variability in performance. So this is very important for us so that we know our lower bound and our upper bound. We also have been doing testing with respect to multiple rows and different configurations with respect to this to assess how the performance of the SEAHIVE systems that we propose can change. Here you have some reef units and at different spaces, and we have some work that will come out with respect to the parameterization of this. And of course, we do, our collaborators, Royal, we do numerical studies when it comes to the wave energy dissipation. So this is work from UC Santa Cruz, where they have been modeling the performance of SEAHIVE and other units and other technologies on the reference project. Now, when it comes to our center, and this is tying back to our activities, we have been testing the SEAHIVE units under compression and bending to assess their performance with different manufacturing methods. So here's an example. These are this is with respect to what was presented earlier in our center. So this is the SEAHIVE project in collaborations with Texas State. So we are testing the units to assess their structural performance, their structural strength as a unit. And of course, we have different ideas and designs in mind when it comes to how we reinforce and how we produce those units. And these are very important to be tested because then we can know what are the limitations of the units, and then we can talk about the system also performance. On the same time, you all know that there's been this idea of using SEAHIVEs for scouring. So this is work in collaboration with Texas State, and what you see here is their work in terms of comparing a SEAHIVE with a monopile, but also extending to a SEAHIVE system. So we might need to make some design adjustments when it comes to the scouring protection but the preliminary results that we've seen are promising. So this is a work in progress. Now, of course, as you understand, this is a very large project. It started with the investment of TRB from the SEAHIVE project and the collaboration with the Florida Department of Transportation. But this has extended and reached beyond, way beyond that. So this is a collaborative project, and a lot of players and organizations are involved. And I would like to thank everybody. And of course, our collaboration with the Florida DOT and the center here is promoting this further for future endeavors. Thank you.
All right. Yeah, great. Thank you to both presenters. Yeah, both presenters are here. I think we have approximately 4 minutes for Q&A. Do we have any questions from the audience? Yeah, I don't see any questions. Yeah, I guess it's a Friday, right? All right. Okay. Yeah, I do have a question. So those are great innovations. So I know Plient Fibers, Charles has been using it for pipes. So it's a precast element, and Landolf, for your SEAHIVE, you also need a reinforcement, right? So I'm thinking, is it possible to integrate both innovation together? But what type of research questions we need to answer, or what kind of research we need to do? I think I need input from both of you. So Chaz, can you talk about that maybe from the fiber side, and we'll ask Landolf to talk about from the SEAHIVE side.
Yeah, for sure. So great question, and obviously it's kind of a nice marriage of the two concepts. From the Plient side, the fiber side, purely, performance side, the question would be, what kind of failure mechanisms are you seeing in the SEAHIVE setting? And I think the last couple of slides that Landolf was sharing about some of the structural testing and evaluating the load capacity from a fatigue standpoint, hey, do repeated waves over time, does that generate fatigue damage? Questions like that might be something where, what is your design goals from a reinforcement? Because currently, if you're using rebar, you're trying to achieve some type of strength from that setting. So that would be the biggest thing, and then that kind of helps determine, hey, what kind of dosage are we looking at for fibers? Is that something that's achievable? Everything I talked about in the presentation about savings in terms of time for rebar, the mesh fabrication, all that, and placement can still be achieved for something like a SEAHIVE application. But that's kind of what I would be thinking from a fiber side, is what are the design needs from a structural element from that side. And I have a feeling Landolf might mention some marine applications, so I think maybe he can talk more about from that side.
So definitely the convergence of the two, I would say, ideas in presentations. By the way, it's awful to see yourself in the video and pay attention.
It's so bad.
Yes. So, I mean, Stacy, you're going to regret this at some point, but the idea, I mean, you can see that these ideas are basically, we can converge, obviously. There are a couple of things. The capacity is the obvious structural question that we're all thinking directly, but there are some other aspects that we also need to investigate in terms of the durability, in terms of the compatibility with the marine environment, that are important for the applications that we use them. If you take SEAHIVE as a structural element out of its environment, which for us is the coastal environment, then obviously I think there is no issue with the fibers. I mean, we do some structural testing right now, both 4-point bending and some compressive test to assess the capacity that we're getting with those rebars. The other thing that we need to consider maybe is the fabrication method, how we cast those units, how are those fibers, maybe a good way of getting away from discrete reinforcement, if we can get away from some applications. And we can see that maybe that the technologies are compatible in some applications versus others, or I mean, promote kind of like a niche area where we do something like, and again, some ideas here I think are going to be definitely things that we will explore in the future through the center or other, let's say, opportunities. And yes, with respect to Susan's question, yes, there is reinforcement. So we use non-corrosive reinforcement. And the idea is that not only we avoid the corrosion issue, especially on the applications that you have the direct dry, those cycles between exposed and non-exposed to salt water, but also it is to avoid the issues with corrosion and the biocompatibility.
All right, great. Yeah, I think we're right on time. And yeah, so that's it for today's webinar. And yeah, we'll be posting the video online and we'll be able to share with everybody. All right. All right. Thanks, everyone.
Thank you,
Happy
guys.
Friday.
Thank you. Thank you for giving us a chance to talk.
Bye.
Thank you for your time.